All right, we're going to start with just a summary of what you guys talked about in the last class, which are these various methods for sampling distributions that are represented by a Bayes net. Can someone tell me which of these distributions is for sampling joint distributions as opposed to conditional distributions? If you look closely, you can actually just see the answer, which I noticed midway through asking that question. But yeah. So prior sampling is if you want to sample the values of all the variables not conditioned on anything. It's easy computationally to do this. This is exactly how the Bayes net is structured to make this easy. You start at the top. You sample variables with no parents, and then once all the parents of a given variable have been sampled, you can sample that. The conditional probability table tells you exactly the distribution under which to sample the variable, and then you keep going down through the net. But there isn't such a logical procedure for sampling if you want to condition on variables that are potentially midway through or towards the bottom of the Bayes net. Because even though the parents of some evidence variable will, you can learn about the parents given the evidence variable, that's not how the conditional probability table for those variables are structured, so you have to do clever things. The least clever thing is rejection sampling, where you just sample from your prior and you keep sampling until you get something that matches the evidence. And if you guys remember from when we did that game a couple weeks ago, when there were those conditions where somebody won when the event sunny happened, condition on it being hot or something like that. What I did was I just sampled from the whole distribution and kept sampling until the sample matched the evidence. And so what we did there was rejection sampling, most basic technique. And here's a nice little picture where you're sampling just from the, is this? Yeah, okay. You're sampling from the prior distribution, so it's the same as prior sampling, but then you're just throwing out some samples if they don't match the evidence. Likelihood weighting, instead of throwing out samples that don't match the evidence, you don't sample the evidence variables because you know what they're supposed to be, but you downweight if you're in a situation where that evidence variable was actually pretty implausible. So in an extreme setting where the probability of an evidence variable was 0 given its parents, you do your prior sampling, you get to its parents, and now you downweight all the way to 0 because there's no chance of observing the evidence that you're trying to condition on given its parents. But maybe it was not quite that unlikely, it was just moderately unlikely, so you downweight according to the probability of the evidence variables, rather than just trying to sample it and see if you end up with the right answer and throw it out if not. That's a noisier thing to do. And then Gibbs sampling, which is the coolest, is you start with your evidence variables having the right value, and you sort of slowly change. You slowly change the values of other variables. And you do this in a way that ultimately the distribution you end up with matches the conditional distribution. And actually, after today's lecture, that method will hopefully make some more sense. Okay. Some announcements before we get on to the next topic. As I hope you guys all know, there's a midterm on Tuesday. There is a special review session for it tonight from 6 to 8 p.m. You can look on Ed for the details, and the worksheet for that session should be available already on Ed. And so, to the extent that you're feeling more concerned about the midterm, it might help to look at that in advance and know what questions you might want to come in with. Okay. Any logistical questions or questions about Bayes-net sampling? Great. Okay. The next topic is Markov models. So in Bayes-nets, there isn't any special structure for things changing over time. And this is what we're going to introduce now. So often we want to reason about a sequence of observations where the state of the underlying system is changing. This happens in speech recognition, it happens in robot localization, user attention, medical monitoring, global climate. All of these things, they are sort of things you can track over time. They have non-zero relation. You know, the state at time t has non-zero relationship to the state at time t minus 1. There's some form of continuity. Or if things are changing rapidly, at least they're changing rapidly in consistent ways. So, you know, if you have a sound wave, the pressure is rapidly changing between high pressure and low pressure as a sound wave passes you by. But the way in which it changes is stable over time. So now we're going to introduce time explicitly into our models. So this is kind of just like a less general framework than Bayes-nets, but it's such a common thing to have things change over time and a natural way to think about it that it's helpful. And actually, there's one way it's not less general, which I'll get to in a minute. Okay. Markov models, also known as Markov chains, also known as Markov processes, work as follows. We have a value of some variable x at a given time, and that's called the state. Usually, and for the whole of our discussion, I think, at least the whole of our discussion today, the state will be discrete. There will be a finite set of values that it can take. Countable also qualifies as discrete. I'm not sure if we're going to deal with any of those cases. Not that I can think of. Okay. So we have our variables, x0, x1, x2, and so on. And what do we, and the graph, the graphical model looks like this. So all we need to specify the distribution over these variables, well, we need the probability distribution over the various values that x0 could take. And then for x1, we just need to say, given the value of x0, what is the probability distribution for x1, and so on. So here's what we're given in the Markov model. And what we'll be discussing for the next several slides is how we can compute other values of interest given these pieces of information. So the transition model, probability of xt given xt minus 1, specifies how the state evolves over time. These are capital letters, so who can tell me, let's say there are 5 different values that xi could take, or xt could take for any value of t. How many numbers are in this transition model? Yeah. Yeah. So for every possible value of xt minus 1 and for every possible value of xt, this this term denotes a value for all of those. So it's a two-dimensional thing because there are 2 capital letters. The assumption implicit in a Markov model is that the transition probabilities are the same all the time. So states aren't necessarily constant, but the way that they affect the next state is constant. Then there's the Markov assumption, which is encoded in the structure of this graph. which is that the future is independent of the past given the present. If your attention was drifting, pay attention. That's a profound and important observation, and it's critical for making reasoning tractable. So the future is independent of the past given the present. This is a statement about conditional probabilities. And let's recall what that means. According to the Markov assumption, if you know everything about the present, learning about the past doesn't help you predict the future. And in theory, this is true in the real world. If Heisenberg uncertainty principle aside, you somehow knew the position and velocity of every particle in the universe, and you were interested in predicting the future, you shouldn't have to look to anything in the past to help you predict how the universe would continue to evolve, at least according to what I take to be a standard understanding of physics. So it's obviously the size of the state for which the Markov assumption holds is unreasonable. But in some settings, it's more reasonable than others. We can try to come up with states that are keeping track of the relevant information so that we don't have to, when thinking about making predictions into the future, consider how a vast history of observations might affect that. If the state can capture everything that was worth having learned from the past, then we don't have to keep going back to it. We can have a contained object that's sufficient for making predictions about the future. So that's the Markov assumption. Hopefully the intuition about physics gives some intuition for why it might be the case in systems where the state space is very large. Yeah? Uh-huh. So imagine that I didn't give you 25. Okay, so what I said maybe quickly was suppose x can take 5 different values. And let's say that you understood that that the probabilities for the 5 different values were 0.1, 0.2, 0.3, 0.2, and 0.2. And now you wanted to know what the probability distribution over the 5 different values at x1 were. You'd have to think about, okay, so what are all the possible values for x0? And then given those, what's the conditional distribution over the next one? So you'd want to know, okay, so if x0 took the first, let's index them 1 through 5. If x0, we were in state 1, what's the probability distribution over all 5 states? Okay, that's 5 numbers. If we were in state 2 at x0, what's the probability distribution over x1? That's another 5 numbers. I've left out the fact that you actually only need 4 because you can subtract the sum of the others from 1, but roughly n squared. Other questions about any of these 3 bullet points? Okay. So, putting that Markov assumption in symbolic language, xt is independent of everything xt plus 1 is independent of everything prior to xt given xt. And technically this is a first order Markov model. If I just say Markov model, you can take me to mean first order Markov model. A kth order model allows dependencies on k earlier steps. We haven't talked about reinforcement learning yet, but maybe some of you have heard of it. In some recent reinforcement learning systems where the the system is getting observations that don't actually tell it the whole state. They just kind of pretend that if you look at the last 4 states, the last 4 observations, that does, and it's a bit dubious. But it does make it a little easier to make this assumption if you're conditioning on a few more states in your recent past. An example from physics that might make this intuitive is, I mentioned the positions and velocities of all the particles, but if you looked backwards a nanosecond, you could just look at the positions, because then you could kind of interpolate the velocities. So if you just look at the positions at this time and a time right before, now your state space is smaller, and even so, a second-order Markov model is reasonable. Okay. We're basically just going to talk about first-order Markov models, but you could extend this pretty easily to kth-order Markov models. Okay, so the joint distribution between the set of variables x0 through xt will take this form. The probability of x0 times the probability of x1 given x0 times the probability of x2 given x1, and so on. It's very close to just the definition of conditional probabilities, but if we added here x1, x2, x3 up to xt minus 1, then this would just be true by definition. And so the only bit of work that we're doing here is noticing we can cross off those extra things in the conditional side of the probability because of this Markov assumption. Okay, so here's a little quiz question. And I got a little ahead of myself a couple slides ago. Are Markov models a special case of Bayes nets? Just think about that for a second. Yes and no. Yes, there are directed acyclic graphs, and the joint is the product of conditionals, so every variable's distribution is defined by a conditional probability based on its parents, in particular its parent. But there are a couple ways in which they are not really. There can be infinitely many variables. Bayes nets require finitely many variables. And the repetition of a transition model is not part of the standard Bayes net syntax. So if you had infinitely many variables in a Bayes net, it would take infinitely long to write down the whole specification of it, because you'd need to rewrite it for every variable. And so here we have infinitely many variables, but we can describe it in finite length by specifying that there are some variables that are substantially similar to others. In fact, their conditional probability tables are basically identical, but with a different parent. Okay, let's look at an example of a Markov chain. So let's say we are doing a random walk in one dimension. We start at 0. And the state is just where we are. And think about it for a minute. I'll give you a little more specification. So with probability 1, it starts at 0. And then the transition model is 50-50. It increases or decreases by 1. So we can think about the Markov assumption and check for ourselves that it holds. If I tell you that at time 5, I'm at -2, and you want to know the probability that I'm at -4 at time 50, it's not going to help you to know where I was at time 4 or 3 or 2 or 1. The information about where I am at time 5 makes all that other stuff unhelpful. You don't care about how I got to where I was at time 5 if you're interested in where I go from there, because no matter how I got there, where I go in the future follows the same distribution. So there are applications to this very simple Markov model: particle motions in crystals, stock prices, gambling, genetics, and so on. And we can consider questions like, how far does it get as a function of t? Obviously, this will be a random variable, not a deterministic function. Turns out the expected distance is order the square root of t. So if you quadruple the amount of time that this runs, in expectation, it'll be twice as far from where it started after 4 times as much time. Another question that we can consider is, does it get back to 0, or can it go off forever and come back? Or with what probability does it get back to 0? Any guesses? Who thinks more than 50% it gets back to 0? Who thinks less than 50% that it gets back to 0? Okay. Okay, people who thought it was more than 50% likely to get back to 0. Who thinks that it's more than 75% likely to get back to 0 at some point in time? Yeah. Yeah. I don't remember exactly how many people were above 50% and lower than 75%. But in fact, with probability 1, in 1 dimensions and in 2 dimensions, it will return to where it started eventually. Maybe it'll take a very long time. I can't remember if the expected time is finite or not. I'm going to guess finite, at least in 1 dimension. But in 3 dimensions, weirdly, it returns with probability 0.3405, so on. This is, I mean, it's cool. Like, there's lots of interesting math from a pretty simple formalism. Yeah, we won't come close to figuring out why any of these results happen in this class. But there you go. Very simple model, and pretty quickly there are some interesting and complicated questions to ask about the distributions of random variables way down the line. Okay, here's another example of a Markov chain. These are called n-gram models. Have any of you guys played around with Google n-grams? That's like the thing where you type in a word or a phrase and you look at how common it is in books over time. So that data set that they've collected is this kind of thing you'd put into an n-gram model, which is why they call it that. Just keeping track of counts of sequences of variables. So in that setting, the state variable is what word, over time is like over position in the document. Okay. There's a little quote. I'll skip it. So the state for an n-gram model is the word at position t in the text. You could also do it over letters, but that's not really the right way to chunk text. And then there's a transition model, and the probabilities can come from empirical frequencies. And so this is what people at Google did, I think, in their spare time. They collected these empirical frequencies over, you know, however many decades they were looking at. So a unigram model, a 0-order model, is just the probability, the probability of word t being I doesn't even depend on anything. It doesn't depend on the latest word. It's just the same probability at every time. So you're basically sampling according to word frequencies. It's not a very good model. Russell and Norvig tried this out for the text in their textbook. They built a unigram model of the textbook by just looking at the word frequencies in the textbook, and here's a sample from it. Logical are as are confusion, a may, right, tries, agent, goal, the was. So there's no structure here, and there shouldn't be, because the probability that I sample confusion here has nothing to do with this word before it. A bigram model is a first-order model, and this is so a first-order Markov model. This is the kind of thing we're going to be talking most about. So the probability, what you're keeping track of is the probabilities that word t equals I, given the probability that word t minus 1 was j, for every I and j. And when you train that, on pairs of adjacent words in the AI textbook, and then you sample from it. You get something like systems are very similar. Computational approach would be represented locally. It has some sensible structure, but it falls apart pretty quickly. So you can kind of, it's interesting to look at. It's like systems are very similar. Yeah, okay, very similar. It's kind of working over here, but then very similar computational approach. Yeah, that makes sense, but then it doesn't hold together more broadly because these words, when they're sampled, aren't considering what happened even 2 words before. Triogram looks a little better. So this is a second-order Markov model taking account of the state at the previous 2 time steps. Planning and scheduling are integrated. The success of naive Bayes models is, so okay, I mean, that's good. Like the probability of Bayes clearly went up after naive. You could have gotten that out of a bigram model as well. So you can see how this is working. Can anyone think of a simple way to turn a second-order Markov model into a first-order Markov model? Yeah.
Use the chain rule. Say like probability of word t minus 1 say equal to what t minus 2 0.
Yeah, so you could do that for computing it. The question might not have been clear enough. Because it still wouldn't exactly have the structure of a first-order Markov model, but what you could do is just square the size of the state space. So the state could just be, so you have your low-level states where the second-order Markov assumption applies, and then you could have higher-order states where they're actually pairs of sequences of states. And now just conditioning on the previous one would effectively be conditioning on the 2 previous lower-level states. But it comes at the cost of making the state space much bigger. So if you're thinking about, you could say, okay, you could do letter n-grams, you could do word n-grams, you could also do word pair n-grams, and then that would amount to basically making first-order versions equivalent to second-order versions in the other one. Bit of a digression. Okay. Applications to n-gram models include text classification, spam detection, author identification, language classification, and speech recognition. So here's a simple way you could try to detect whether a piece of text was written by one mysterious author or another mysterious author. You could train an n-gram model on both of the author's works and see which predicted a higher probability for the text that you're trying to learn about, to see which one of them, whose style it better matched. Yeah?
How do you decide which word is I, J, and K? Like, do they have to be next to each other? Or?
They don't have to be next to each other. T and T minus 1 have to be next to each other, but this is, they're capital letters, so it's, well, okay, no, the notation's a bit confusing. It's all I and all J. So you need a number for every pair. So you need a number for every pair of words. You need a number for every triple of words. The probability that word I follows word J, or the probability that word I follows word J followed by word K. So this, I mean, it's starting to get to be a big object, the number of words cubed. Yeah?
But could you keep going for a long run on the road?
Sure, yeah. But as I just mentioned, I mean, okay, how many words are there? Like tens of thousands. Raise it to the power of 4. I mean, even if you can represent the table, you probably don't have good data on the frequencies that are appropriate. So yeah, it won't always just improve because the quality of the transition model will deteriorate because you'll need more data to fill it in well, and you won't have that data. So with a finite amount of data, it's not like you should just increase this arbitrarily. I mean, suppose you had a 1 million gram model Well, for most sequences of 1 million words, they've never appeared before in the whole history of text. And so if you're trying to come up with probabilities based on what you've seen before, you just kind of maximally uncertain, if that's all you're going off of. Okay, another example of a Markov model is web browsing. So the state in this little toy problem, not such a toy problem actually, the URL visited at step T, and the transition model is with probability P, choose an outgoing link at random. With probability 1 minus P, choose an arbitrary new page. Question, what is the stationary distribution over pages? That is, if the process runs forever, what fraction of the time does it spend on any given page? And I say not such a toy problem because a key application of this was Google PageRank. I learned recently actually that this page is named after Larry Page, not like web page. There's a little fun fact for you. And so this is the algorithm that Google used to, and probably to some extent still uses, although I bet they've done some fiddling with it, to prioritize which pages to show people. I mean, so you still have to evaluate which pages are more relevant to a user's query, but this is kind of your prior probability about among pages that match a user's query, which should you prioritize, and they suggested that, or they worked on the assumption that it would track states that were commonly visited on this Markov chain. And that position seems to have served them well. Okay, third example is the weather again. So our states here, we only have 2 states, rain and sun, and we have some initial distribution, initial probability distribution at time 0, what's the probability of rain and sun, and then we have a transition model, and the transition model takes into account that if you have a rainy period, if there's rain one day, it's a little more likely that there's rain the next day than if there's sun, and if there's sun, it's a little more likely that there's sun the next day than if there had been rain. So here's the conditional probability table. If there's sun at xt minus 1, then the conditional probability over xt looks like this. If there's rain at xt minus 1, then the conditional probability table over xt looks like that. And so you sample from it, and you might get something like this, where the sunny periods and the rainy periods are a little more likely to be clumped together than if each were sampled independently. So here's a kind of visually, I won't go so far as to say painful, but visually unexciting way of representing conditional probability tables. Here are 2 new ways to represent them. So we have rain and sun, and this is representing the probability of transitioning back to rain versus transitioning to sun. Here we split it up over time, so this kind of, well, there's pluses and minuses, but sometimes you want to look at variables' values at different points in time and in separate locations on your diagram. But here's another way of representing the same thing. Any questions up to this point? Okay. So let's do an example of computing, given that model I just showed you, the probabilities of rain and sun at various different points in time. Time 0, easy, given. What's the weather like at time 1? What's the probability distribution over the weather? So here's what we want, but the information we've given isn't in this form, so we need to do some tinkering with this. First bit of tinkering is to note this equivalence. So the probability of x1 is equal to the sum over values that x0 could take of the probabilities of x1 and x0 taking that value. So this is like the opposite of marginalization. Marginalization would be going from right to left, and here we're, I don't know if there's a word for it, unmarginalizing. We're introducing a new variable and summing over it. So the probability of x1 The probability that it's sunny at x1 is equal to the probability that it's sunny at x1 and sunny at x0, plus sunny at x1 and rainy at x0, summing over all the possible values at x0. And this, now we split that up, this joint probability, into the probability of one of the variables times the conditional probability of the other given the first. So here we have the probability that x0 takes value little x0 times the conditional probability distribution over x1 given that conditional. And these are all numbers that are given to us in our Markov model. So note that these are going to be, for each term in the sum, this is a number, because we're talking about the probability of a lowercase thing. And this is a vector, because it's a probability distribution over the value of this random variable. So we have 0.5 times this vector plus 0.5 times this vector, and that's going to give us a probability distribution like this. So given this transition model and this model of the initial distribution, this ends up being the resulting distribution at time x1. Maybe it's a bit of a boring bit of computation, but this is how you do it. We can do the same for time 2. We can forget about all that math we did. We don't have to redo it. All we need to keep track of for going forward is the distribution over the state at time 1. So then we do exactly the same thing, but now 0.5, 0.5 here has been replaced by 0.6, 0.4. Same bit of math. And we run it again, and now it's a little more likely to be sunny. So even though it started out 50-50, sunny and rainy, you can see here that sun persists a little more reliably than rain. Sun persists with probability 0.9, rain persists with probability 0.7. So on average, some of the rain probability will kind of leak over. I don't know if that's a good way of describing it, but you can see the probability of sun is going up. And it goes up again, but more slowly. It looks like it's approaching something, and it is. So we run the same thing again, and yeah, you can see how it's updated a little bit from time 2 to time 3. And indeed, it will reach a stationary distribution, which is the limiting distribution over time. Any questions? Cool. Okay. So what I just showed you was basically running what's called, well, it's a simple form of the forward algorithm, but I'll describe it in more generality now, even though you've just seen an example, and I imagine that made as much, yeah, I imagine that explained it to you, but I'll just describe it in symbols. It's very important to understand this because there's going to be a more complicated version of this for a more complicated setting, but it'll help a lot if you understand exactly how this works. Okay, so the simple form of the forward algorithm in this setting, here's a reminder of what we have to start with. This is what we're given. And here's what we're trying to answer. What is the probability distribution over the state at time t? So this is a simple procedure for doing it. Okay, in blue, well, this is going to be an iterative algorithm. So the way we're going to compute the probability distribution over the state at time t is by first computing the probability distribution over the state at time t minus 1. The way we're going to do that is by first computing the probability distribution of the state at time t minus 2, and so on until we get back to the distribution over x0, which is given. Okay, so here's what we're trying to get. This is the same thing I showed you in the last slide or 2 slides ago. And this is the same thing, except now it's not numbers, it's symbols. But this is the same deal. So we're doing the opposite of marginalization here, and then we split it up like this. And if you want to know why we took this weird step of unmarginalizing it and why we chose this way of splitting this joint into a product of a conditional and kind of a just a probability distribution over one variable? Well, it's so that it would take this form. This is something that we have. This is something that is given in the problem statement up here. And this is kind of the equivalent question about the previous time. So that's the probability from the previous iteration, the probability distribution over xt minus 1, and that's the transition model. So we can iterate this update starting at time t equals 0, and it's a recursive update. So we know how to get from, since we know how to get from k to k plus 1, we can bring k from 0 up to t and get all the way up to t. So this operation, all the stuff in pink, turning this blue thing into that blue thing, is captured by the function g. Okay, this is the attendance code, and this is what you can think about while you're doing it. Any questions about this forward algorithm simple form? Yeah.
So, does this have to do with like the clumping thing we were talking about earlier? Like more likely to be grouped together? Like, or is that separate?
Clumping.
When you mentioned the weather, like the same.
They're more likely to persist.
Yeah.
Well, that was like a qualitative assessment of that particular transition model. You could imagine a transition model where it's more likely to flip. So this is since this is a general updating strategy, if there is a clumping effect, it will capture it. But if there isn't, it'll still work fine. Yeah, if you want to, you can try to think through a situation where it's highly likely that states persist and kind of see what this calculation would look like. So if we're in a situation where it's very likely that states persist, then if we're looking at the probability of sun here, that's going to come from a term when this was rainy versus when this was sunny. But since this is going to be so small when this is rainy, most of the probability is going to come from the term when this was sunny. Probably a lot to say without drawing anything down, but there you go. Any other questions? Okay. So you can use the language of linear algebra to write this down as well, which can make it, well, there are a few reasons. You can make it run faster if the matrices are really big and you want to use GPUs, or it'll help do analysis about the stationary distribution. Okay, so this probability being, here's a scalar, here's a vector, and we're writing it down this way. We can write it down in matrix vector form like this. So, you do this, to get this element, you do this row times that. To get this element, you do this row times that. This is how matrix multiplication works. That's nice. Matrix multiplication has been studied extensively, to put it mildly. So what we do is we multiply by the transpose of the transition matrix to go from the probability distribution at one time to the probability distribution at the next time. If we had written this, obviously if we'd written that in a different way, then we wouldn't take the transpose. But the way we've been writing down conditional probabilities tables in this class, you take the transpose of them. In reality, you just have to stare at it painstakingly to make sure that you were doing it the right way. I hate when Torch, NumPy, you just always have to, honestly, I write code and it's just like 50-50 whether I've done the transpose the right way or not, and then I see if it works, and if it doesn't, I try taking transposes of things that maybe I should have taken the transpose of, and see if that fixes it. So that's the right way to write code, just for all you guys learning out there. Okay, stationary distributions. So the limiting distribution, and I haven't proven to you that it exists, but let's talk about it anyway for a second. The limiting distribution is called the stationary distribution, and that is the limit as time goes to infinity of the chain. So there's a nice little picture. And it satisfies, if you'll allow for whatever that means, it satisfies p infinity equals p infinity plus 1, which is t transpose times p infinity. And so in this example, solving for p infinity with these matrices, we set it up like that. We can just look at this top row because since everything sums to 1, it turns out if we solved this one, it would give exactly the same information. So that's nice. That's an equation, one variable. There's the answer, 0.75. And you could see, if you remember, they were kind of approaching something like that more and more slowly. And in this setting, there is actually a single stationary distribution. You can write down Markov chains where there are a couple different stationary distributions, well, as many as you like, really, that could be fixed points, and it depends on where you start. Okay, if you remember back to Gibbs sampling from last lecture, I'm not going to go through a real proof of why it actually samples from the right conditional distribution, but at a high level, the reason it works is because it follows a Markov chain with the following properties. So the states are assignments of values to variables in the Bayes net. The transition probabilities are easy to calculate. They only use local information. So it's hard to know from a Bayes net what's the conditional probability of this variable given this variable way over here. That could have, complex effects. It only uses local information, and that's the sort of information that's either given by the Bayes net specification or easily calculable. And finally, critically, the stationary distribution over states equals the desired conditional probability distribution. So these are the key features that make Gibbs sampling work. There's some distribution you want to sample from. You construct a Markov chain with these properties, with these two properties here. And the key fact is that whenever we modify the value of xi, the ratio of transition probabilities for transitioning to little xi versus little xi prime is equal to the ratio assigned by the true conditional probability distribution we're trying to sample from. So we had these evidence variables, and we're sampling basically the rest of these, and this ratio, the ratio of transition probabilities in, is equal to this ratio here. And this ratio here ends up being computationally easy to compute because everything that's not local information cancels out. So that's at a high level why the algorithm works. If you want to know more, check out the textbook. Okay, that's Markov models. Now we're going to go to hidden Markov models. So before we do, it would be a good time to pause for any questions about Markov models. Okay, yes?
So there's no clear answer if it's the same as a Bayes net. It's like that has some properties but not exactly.
Yeah, so I guess the answer is no, technically. It is not the same because there are slight extensions, yeah. But really the only extension is really that it can be infinite, and yet it admits a finite description. Okay, hidden Markov models accommodate the fact that it's usually unrealistic to observe the whole true state. So remember, for the Markov assumption to hold, it has to be useless to consider the past if you already know the state. And that entails that the state captures quite a lot of information, basically all the relevant information about the past that will be useful for predicting the future. And that is such a vast object that we couldn't begin to, I mean, even if it were in front of us, we couldn't read it. I mean, it's just too big. So for any reasonable system, it will only be able to observe bits of evidence that depend on the state rather than the whole state. So that's why we need algorithms to work with hidden Markov models. And while it's still a simplification of the real world, while our actual hidden Markov models will still be simplifications of the real world, it ends up being a much more general model and allows us to get closer toward reasonable modeling. So we have an underlying Markov chain over states, X. And then we observe evidence at each time step. And of course, the evidence, well, at least we can do interesting modeling if the evidence has some relation to the underlying state. So we'll say in this formalism that xt is a single discrete variable. And we may as well say that ET can be continuous. It won't really make things harder for us. It may consist of several variables. So here is an example of a weather hidden Markov model. And the story behind this model is, imagine that you are stationed in a nuclear bunker way below ground, and every so often your commanding officer visits, and you see that he is carrying an umbrella or not, and that is your only information about the weather in the world above, because you're so far below ground. So this state is hidden, and these are your observations. Turns out I have an umbrella today, coincidentally. Well, not entirely coincidentally, conditioned on the weather. Okay, so the hidden Markov model is defined not just by these two things that we had in the Markov model, the initial distribution and the transition model, but also the sensor model. How do the evidence variables depend on their associated state? So here is the transition model, and here is the sensor model. So true, there is an umbrella. False, there is not an umbrella. And how many of you have umbrellas here? Even though it's raining. So some of you guys, it rains and you don't bring an umbrella because I guess, well, it's not raining that much, is it? So given rain, it's not going to be probability 1. I think the commanding officer here is more reliable in bringing an umbrella when it rains than the average person here. But it's imperfect. You don't get to see the underlying state precisely. So now the sort of question, we'll be interested in answering more complex questions because it's a more complex problem. So there's our hidden Markov model. And now the joint distribution for the state variables looks like this. It's the probability of the initial one, same as before, times the probabilities of each one given its predecessor. And, oh yeah, sorry, that's just the Markov model. For the hidden Markov model, where we have the evidence variables as well, then we have this same bit of structure here, times the conditional probability of whatever the evidence is at time t, given the state at time t. And again, the future states are independent of the past, given the present. That's the Markov assumption. And, reading this out as you would a Bayes net, the current evidence is independent of everything else given the current state. So just as once you know the current state, it's unhelpful to learn about the past for predicting the future. It's also unhelpful to learn about the past for predicting what evidence will come out. Question for you guys: Are random pair of evidence variables independent of each other? Shake your head or nod your head. I see like 2 or 3 people shaking their head and nobody nodding their head, so that's good. I mean, as it goes. Take a stand, guys. They are not independent of each other. Think about it this way. If you know that, there tend to be long periods of rain and long periods of sun, and your commanding officer comes down with an umbrella, you can expect that he'll come down with an umbrella tomorrow. I mean, more likely than not. You won't know for sure, but you'll certainly have learned something. So because you can learn about one piece of evidence from another, they're not independent. They're only independent if you condition on a state that comes in between those evidence variables. Yeah?
How can you tell they're dependent from looking at like a graph with the arrows? Does that say?
So in fact, I spoke too soon. It depends on the conditional probability tables, but if you randomly sample a conditional probability table, they will be dependent. Yes, you can look at the graph to know this. It gets a little complicated, and we're not going to go into it, but come up after and we can talk about it, or you can look up probabilistic graphical models. You can look up Judea-Pearl. There's a big literature on this. Basically they're connected. In general, let me make sure that's right. They share ancestors, I think, is enough. If you're just looking at whether they're independent of each other, I think if they share an ancestor, then they're probably not going to be independent unless you have very particular conditional probability tables. But there's a whole, if you're trying to figure out exactly what conditional independence claims you can make given a graph, it gets a little more complicated. If we're just talking about independence, I think it's enough to say if they share a parent, they're probably going to be dependent, an ancestor.
Could you say like they all have an ancestor next to 0?
Yeah. So basically all of these are in general going to depend on each other, but there are still going to be conditional independences. Does that sound right to you?
Yeah.
Okay, great.
Even on these separations,
Right.
you can look at the past.
Yeah. Okay, cool. Okay, here's some useful notation for going forward. X, A to B is just going to include all of these intervening variables. Okay, some real hidden Markov model examples. Speech recognition. The observations are acoustic signals, and the states are specific positions in specific words. So we're not observing the words directly. We're just observing the sounds that they produce. And certain words are more likely to produce certain sounds. Machine translation is another application of this. That's a little, it's a little harder to see how this can be models in HMM, but the observations are words here, and the states are translation options. So if you're trying to translate, say, French into English, using a hidden Markov model in this setting would be kind of like thinking in English and thinking about, okay, how likely, if that was the, real language starting point, that you'd come up with this foreign text. I think that's the best way to think about it as a hidden Markov model. You might be able to do better by allowing yourself to think in either language, but if you're just thinking in one language and thinking about what kind of text in the other language that would produce, then you can think about using a hidden Markov model. Robot tracking, the observations are, whatever sort of sensory inputs that it gets, and the state is a position on a map. Obviously, it doesn't get to observe that directly, it has to infer it. While the Markov assumption is a bit dubious here, knowing a specific word does not actually tell you everything about the future. Like, it would help to think about what other words were coming before. Here, the Markov assumption is pretty reasonable. If you know where you are, and then what observations you get after that, it doesn't really matter so much how you got there. But even so, it's not fully reasonable to make the Markov assumption here. Maybe in your past you learned about obstacles in various spots that you can expect to encounter again. So all this is to say you can use a hidden Markov model even if the Markov assumption isn't fully valid. Just don't complain too much if it doesn't work. Last example, molecular biology observations are nucleotides, and the states are various high-level things that can be happening at that point in the genome, like coding, non-coding, starting, stopping, splicing, etc. Okay, now what are some questions we can try to answer if we have the hidden Markov model and we want to play around with it? Or, use it to do useful things in the world. First one is filtering. So we have evidence from time 1 up to time t, and we want to know what state we're in. And this could be useful for doing all sorts of things, like prediction. This could be like a step in prediction. But the prediction problem is slightly different. We're trying to predict what's going to come next, given what we've seen so far. And this is for k greater than 0. So this could look like evaluating possible action sequences, and it's like filtering without some of the evidence, because we haven't gotten the evidence between t and t plus k yet. Another inference task we might want to do is smoothing. So now note that k is less than t. We're trying to figure out what was a state in the past, given everything we saw up to then and past then, up until now. Better estimates of past states, and this is essential for learning from past states. And finally, an inference task we'll talk about is coming up with the most likely explanation. So we're coming up with a sequence of states that is maximally likely given the sequence of observations we made, sequence of evidence variables that we observed. And this is what a speech recognition algorithm will do, or decoding with a noisy channel. If you have a speech recognition algorithm and it gets audio input, there are some settings where you'd like a full distribution over every possible string of text that it might have produced that audio. But in reality, often we won't have time for that, and we'll just want a best guess. And so this is the problem for coming up with a best guess for the underlying text that produced the audio. Any questions about these inference tasks? Okay. Here's little pictures of them, which is probably the most helpful way of looking at it. These are the evidence variables. This is what we observe in lowercase, so we get to see their actual values. Filtering is about predicting this, prediction's about predicting that. Smoothing is in the past, and explanation is coming up with one whole. And, well, the way it was presented in the last slide, it's not really coming up with the distribution, just something that maximizes it. So it's useful to keep track of what's going on. And so this is what the filtering or monitoring problem is. Filtering, monitoring, state estimation is maintaining a distribution as time goes on of what the hidden state is now, because the hidden state can tell you everything about what's going to happen in the future, if only you knew what it was. So we start out with an initial f0, some distribution over the hidden state at time 0, before we've seen anything. That's standard to just kind of get things going. And then filtering is a fundamental task in lots of domains. So for example, the Kalman filter, and we're not going to get into that here because the hidden state is a continuous variable. But the Kalman filter works like that: continuous variables, linear dynamics, Gaussian noise. Linear dynamics just means that if you consider the probability distribution of the next state given the first state being here versus the first state being here versus the first state being here, halfway in the middle, there's a relation in the distribution over the next state. It ends up being like an average of the two on the outside. Invented in 1960, used for trajectory estimation in the Apollo program. Gauss also used it for planetary observations, apparently. I didn't know that. And it has over 1 million papers on Google Scholar, so that's how you know it's important. But yeah, this has been an extremely important algorithm, and computers were not very powerful then, and they could run it, so it's an extremely efficient algorithm. Here's an example of keeping track of the state. Robot localization. We saw something similar when we were talking about logic in Pac-Man, but now we have noise involved, and so we have to have a probability distribution over the state rather than just saying, here are all the states that aren't ruled out logically. So the sensor model here is we have 4 bits, whether there's a wall, north, south, east, and west, but there's some probability of a mistake in the sensor model, but never more than 1 mistake. And then there's a transition model, which is sometimes actions just fail. Doesn't, try to move one direction, but even if there's no wall there, it doesn't end up succeeding. So here is a starting distribution, a starting probability distribution that the robot might have about where it is. These are consistent, these are the most consistent, if I can say that, for the sensory reading, but this is consistent too. It's just less likely because it meant that the sensor down here, which said there was a wall there, was making a mistake. So we have light gray, dark gray, different probability assigned to different states. And now we move that way, or at least send out the move that way action, and maybe it'll fail, maybe it'll succeed. And now here's the distribution over states. This is still possible because maybe it failed, but it's not as likely, and so on. Here's time 3. Here's time 4. So this involved no mistakes, basically. This involved 1 mistake. This involved 2, so it's less and less likely. And now we move there, and now it's really likely that the robot's there. I mean, there's some possibilities that it's in these various other spots, but its distribution is concentrated on the truth. Okay, so now we're going to try to design a filtering algorithm. And it's going to take this similar form to the simple version of the forward algorithm that I showed you before. So the idea behind this is, okay, so we're going to have this quantity of interest, the probability distribution over xt plus 1, given all the evidence up to xt plus 1. Well, suppose we've already computed this kind of analogous quantity at time t. Maybe, and spoilers, it's going to turn out yes, maybe there's some relatively simple update we can do to get from this to this. Obviously, we've gotten more information, et plus 1, so that's going to have to be incorporated. What simple function might this be so that we can get from this to that? Okay, let's do lots of pushing symbols around. So here's our quantity of interest. We can split this up. I mean, this is just the definition of this kind of. I mean, this is all the evidence variables from 1 to t plus 1, and now we're just separating it out into 2 pieces. So we're conditioning on all that. has exactly the same meaning. And now we can apply Bayes' rule. So it's more natural to talk about things conditioned on their ancestors rather than things conditioned on their descendants. That kind of matches what's going on causally. So here we have xt plus 1, that's an ancestor of et plus 1. We're getting closer to the sort of things we can expect to know about if we had et plus 1 on the left and xt plus 1 on the right. So we apply Bayes' rule, so we have this normalizing constant, and now we're leaving e1 to t on the right. On both sides of this equation, everything's just being conditioned on all of this evidence. The only thing is we're moving et plus 1 to the left, we're moving xt plus 1 to the right, and so here we have this is equal, well, it's proportional to the probability of et plus 1 given xt plus 1 and given all this evidence, times the probability of xt plus 1 given all the previous evidence. So this is a simple application of Bayes' rule, just conditioned on some extra stuff, e sub 1 to t in particular. So that's the first step. And I promise you this is progress, but it takes a few more steps to see it. Okay, next step, we apply conditional independence. So the evidence at time t plus 1 only depends on the state at time t plus 1. You can look in this graph here. E4 only depends on x4. If we know x4, it doesn't help to know anything else about E1 through 3. This is encoded in the graph representing our hidden Markov model, that this equals this. We've just crossed this out because knowing about this doesn't tell us anything new once we know this. So that's applying the conditional independence encoded in the hidden Markov model. So this is given by our hidden Markov model. That's good. What the probability of the evidence is given the state. So now we need to deal with this. This isn't given by the hidden Markov model. So this is the prediction step, this is the update step, we can think about it, and this is the normalizing step. Okay, so now what we're going to do is very similar to, well, it's the same as that unmarginalizing step I showed you in the simple version of this algorithm. We're going to sum over the various values that xt could take. So this is xt plus 1 conditioned on the evidence there. And now we are summing over all values of xt, weighted by the probability that that is in fact the value of xt, of the value of xt plus 1 given that value of xt. I'm going to go into more detail on each of these steps later, but this is basically thinking about, it's thinking step by step about the probability distribution over xt plus 1 given the evidence up to t. The idea is, okay, if we're going to try and think about the probability distribution at xt plus 1, let's first think about what the probability distribution at xt is, and then how the one at xt plus 1 would depend on xt. So this is just splitting it up like that. Noting that these evidence variables, E1 through 3, if we're trying to see how this depends on this, it makes sense to think about how that's mediated by the value of this, the value of x3. Okay. And now we do the same thing as before. We apply conditional independence. The probability over xt plus 1 given xt and this evidence is the same as just given xt. This comes straight from our transition model. Knowing the value of x3 means that knowing the value of this evidence doesn't change our distribution over x4. So we can just cross this off, and it's still the same by conditional independence. And what do you know? We've done it. We've converted this into something that's either pre-computed or given by the model. So this is given by the hidden Markov model, the probability of the evidence at time t plus 1 given the state at time t plus 1. This comes from the transition model, and this is what we computed in the last step, the distribution over the previous state given the evidence up until that time. So I'm going to do another round of this at the start of the next lecture, justifying each of these steps. But this is the outline for how this filtering algorithm works, how you do it incrementally, one step at a time, keep folding in new evidence to change your belief, to update your belief about the state. So we have a few more minutes. I guess you guys can go early if you like, or stick around for some questions.